Welcome back. In our previous video, we spoke at length about this idea of limits establishing our foundation for calculus from both a graphical and a numerical approach, which are more intuitive operations. We need a little bit more of a solid approach as we move forward and things begin to get a little more technical. So we have a few limit laws that we're going to establish in this video. So let's say we have two functions, f of x and g of x, and let's say that the limit as x approaches c for both of those functions exists. Okay? If it doesn't exist, none of these limit laws are applicable, but they stem very much back from your days in arithmetic. So we have our sum law, which says if we're taking the limit as x approaches c of f of x plus g of x, we can then split that apart using the addition operation. The same holds true, I guess, and I'll put it in red if you were to do the difference. Next up is our constant multiple law, which says if we have the limit as x approaches c of some constant k times the function, we can rewrite that as the constant times the limit as x approaches c of f of x. Okay? We have our product law, which, as you guessed it, states that if we have the limit as x approaches c of f of x times g of x, we can also separate those limits of the two functions and then multiply them together. And then last but not least, we have our quotient law. That looks like a terrible W. We have to make sure that we are mindful of one key piece here. Alright, so if we have some type of rational function, right? Numerator, denominator, two different functions, we can, once again, split them apart. However, just like in arithmetic, for the denominator, the limit as x approaches c of whatever your denominator function is, here we're using g of x, cannot equal 0. Right? And we typically see this with x values as x approaches 0 for rational functions. So let's get into a little bit of the practicality of this before we conclude this video. So let's say we have the limit as x approaches 2 of x cubed plus 5x plus 7. Okay. Based on our sum law, and right now we're taking a very tedious, arduous approach to calculating limits, we can separate each term of this polynomial. There should be 2 x cubed then here we have 2 to the third power plus 5 times 2 plus 7, which is going to yield 25. So the limit as x approaches 2 of this polynomial is 25. Now if you think back to our initial first two videos, the reason why we were able to take just our limit value and do a direct substitution into the variable is because substitution is only allowable when the function is continuous. If it is not continuous, we cannot simply do a direct substitution. Let's do one more. Limit as x approaches -1 of x minus 6 over 2x to the fourth. So once again, we can split this into two separate functions. And you might be saying, well, Joe, you just said that the function must be continuous, right? At this particular value of c, this function is continuous, right? It's undefined. If we had said x approaches 0, we'd be in a little bit different of a ballpark. So we can once again apply direct substitution into each of these two expressions. And the behavior of this function as the values converge upon 1 would be an output of -7/2. And that's it for basic limit laws. Once again, they're just a more concrete way of allowing us to calculate limits rather than relying on like our intuitive knowledge using, a lengthy number chart or graphical representation.